Back. This is Mr. Hassan's Maths channel. I'm now answering question 7, part B. This is question 7, part B of the February-March 2021 Cambridge Mechanics M1 paper. This is paper 4, variant 2 from the 9709 syllabus. And this question, part B, is dealing with work, energy, and power. So it is given instead that the plane on which Q rests is rough. So we were given this situation in the previous part of the question. And in the previous part of the question, this slope was smooth. Now it's rough. Okay, so there's going to be friction. And that after each particle has moved a distance of 1.1 meter, their speed is now 0.6 meters per second. The work done against friction in this part of the motion is 0.5 joules. Use an energy method to find the value of M. So in this case, M is unknown. In the last part of the question, M was 0.3 kilograms, and it was a smooth plane. Now this is rough, and we don't know M, and we have to find M, and we have to use an energy method. We have to use an energy method, which is very important for us to understand, that we're not going to use dynamics. Okay, we're going to use an energy method. Oops, what am I doing? Okay, so when we use an energy method, we got to think about the work energy principle. So there's a number of ways we could answer this question. We could consider the movement of Q, the energy, the total change in energy, or you applying the work energy principle just to Q by itself. In which case, the problem with that is we'd have to work out the tension in the string, okay? And to do that, we'd have to use this and work out the acceleration and stuff like that. And that's going to be a bit of a hassle, okay? You have to deal with the tension in the string. If we consider the whole system as one, so we consider the overall potential energy, okay, gained and lost by P and Q, the overall kinetic energy change in P and Q, the overall work in and the work out, okay, then we won't have to worry about the tension because that's within the system. We're considering the system as a whole thing. So I think personally the easiest thing to do would be to do just that, to consider the work done, okay, by P and Q, like kind of together, right? So the work energy principle basically is that if you have the kinetic energy at the start of a particular situation, so kinetic energy at the start plus the potential energy at the start plus any work that's going into the system will always equal the kinetic energy at the end plus the potential energy at the end plus any work coming out of the system. Okay, so work going into the system would be something like pulling force, a driving force. Work going out of the system would be something like resistance to motion. Okay, resistance to motion, air resistance, friction, and so on. Right? So we know that kinetic energy is given by the formula half mv squared, and potential energy is given by mgh. Okay, so what I'm going to do is I'm going to consider P and Q kind of separately first, and then I'm going to combine their energy kind of changes in energy. So I'm going to just to make it neater, I'm going to take this and put it over there. And I'm going to take this and put it over here. Okay, so I'm going to consider what happens to P. Now, P is going to be moving in this direction. And Q is going to be moving in this direction. So let's say P starts over here. Okay, this is where P starts. This is P, this is the start. Okay, and P ends over here. I'll call this P dash where P ends. This is the end. And Q starts down here. Okay, that's the start. And Q ends up here somewhere. Okay. So this is Q dash. This is where the end is for Q. Right? And they both move a distance of 1 meter along their respective slopes. So that's 1 meter, and that's 1 meter. 1 meter and 1 meter. Okay, so what I'm going to do is I'm going to consider, I need to know the vertical heights for potential energy. The h is the vertical height through which it's moved. So I'm going to make a little triangle here to help us in order to do that. Okay, so I'm going to make a little triangle. It will help us with the heights for this and this. Okay, so this is a right angle, this is a right angle, this is 1 meter, this is 1 meter, this is 30 degrees, and this is 45 degrees. Okay, and we know that this is the height through which P is moved, this is the vertical height through which Q is moved, so we can say that here sine of 30 equals the height through which P is moved over 1, okay, which is going to be sine 30, which is a half, so that's 0.5 meters. And we can say the sine of 45 is the height through which Q is moved over 1. So that's going to be sine 45, which is root 2 over 2 meters. If you put that in your calculator, I'll put it in exact form, it's better for now. All right, so those are the heights through which they've moved. Okay, so now I know that this starts from here at 0 meters per second, and it ends here at 0.6 meters per second, as the question tells us. Okay, and I know that this starts from here at 0 meters per second, and it ends here at 0.6 meters per second. And I know that there is the work in. The work in is given by the pulling force, which is 0.8 times the distance, which is 1. That's 0.8 joules. And the work out is the resistance force, which is the frictional force, which they've told us. The work done, they've told us the work done anyway, so 0.5 joules. Now, be careful here. If the distance that it moved through was more than 1 meter or less than 1 meter, then it will be 0.8 times the distance it's moved through. Don't just put 0.8. It's not the force, it's the work. And the work done is equal to the force times the distance it moved through. So in this case, it's 1. So even if somebody did have that misconception in their mind, they would still not suffer too much. They would get the right value. Anyway, so be careful of that. Now, the next thing we're going to do now is we're going to consider the energy, like this thing that I mentioned, that you have I need a lot of space here, so I'll just start from here. So we can say that the kinetic energy at the start plus the potential energy at the start plus the work in is equal to the kinetic energy at the end plus the potential energy at the end plus the work coming out of the system. Okay, so kinetic energy at the start. So for P, the start is here, it's not moving. So I'm going to combine both of them. So I'm going to look for P and Q. For P, the kinetic energy at the start is 0, and for Q, the kinetic energy at the start is also 0. At the start of their motions, they're both at rest, as the question tells us. The potential energy at the start, now for P, it's starting off at a higher level. I'm going to call this here, this is the 0, okay, potential energy for both of them, this level here, okay? They're both the bottom levels. All right, so for this case, you got potential energy here, which is mgh. You have m, which is its mass, which was 0.5, times g, which is 10, times h, which is 0.5. mgh, mgh, plus the work in. Now, the work in is basically the pulling force. That's the work in, which is 0.8 joules, as we discussed. So that's 0.8. Okay, and that's equal to the work out, which is the kinetic energy, okay, now both of them at the end, they both have kinetic energy, okay? So for P, the kinetic energy is a half times the mass, which is 0.5, times the velocity squared, which is 0.6 squared. And for Q, the kinetic energy will be a half times m times 0.6 squared. M, remember, is what we have to find. That's the kinetic energy. Then the potential energy is going to be for P, the potential energy is going to be 0. Why? Because it's a 0 level. Okay? But for Q, the potential energy as it's moved up is going to be mgh. So we don't know what m is, so m times 10 times h, which is root 2 over 2. Then you're going to have plus the work in, okay? Sorry, the work out, which is the work done against friction, which is 0.5. And now I've kind of like run out of a bit of space here. Okay, so I'll just put it up here. I should really have planned that a bit better. So 0.5. So this is, before, this is after, and now we have to find m. So everything here is what what we need is here. So you have 0.5 times 10, which is 5 times 0.5. That's 2.5 plus 0.8 equals, you have 0.5 times 0.5 times 0.6 squared. I think I'll need the calculator for that. Okay, so I have 0.5 squared times 0.6 squared, basically, which gives us 0.09. Okay, plus, I'll put this in here as well. Well, I don't actually have anything else. Plus 0.5, don't forget the 0.5. So I'll add the 0.5 to that, plus 0.5. That gives me 59 over 100, 0.59. So I have 0.59. So this that, plus a half m times 0.6. 0.6 squared is 0.36 divided by 2, 0.18 m plus, and this will be 5 times root 2 m. So that's going to be 3.3. So I have 3.3 minus 0.59 over, or I'll just show step by step, is equal to, we have m times 0.18 plus 5 root 2. So I've just basically subtracted this from both sides and taken m as a common factor of these two terms. So m, which we have to find, is 3.3 minus 0.59, which I can actually write down the value of. So 3.3 minus the answer. 3.3 minus 0.59. That gives us 2.71. So we have 2.71 divided by, you have 0.18 plus 5 root 2. So m is going to equal 2.71 divided by 0.18 plus 5 root 2. And, oops, what did I do? Just leave a space and then that's better. Okay, that gives me 0.3737, 0.3737, dot, dot, dot. So m is equal to 0.374 kilograms. So there's the answer to this part of the question. Okay, it says find m. M is, it already mentions a kilogram, so I just put 0.374. Okay, so there's the answer for m. To find the mass of this particular particle, the value of m. That's 7 part B. So this question was all about the work energy principle. Right, so as I said, there's different ways to answer this question. I think this is the easiest way. We don't have to then work out anything like resolving forces, finding accelerations, finding the tension and stuff like that. If we wanted to, we could have considered the work done by Q just on itself. But in that case, we'd have to consider the tension. That would be the work in. Okay, the tension here would be the work in. And to calculate the tension, we'd need to work out the acceleration of the particles, and we'd have to basically consider how this moves with the tension. It's a lot more hassle, okay, I think, personally, although it's a perfectly valid method. I think this is purely an energy method, right, as it asks us to use. So I think it's safer, and it's, a bit easier in that sense. So that's the answer to this part B of question 7. I hope that was clear. Other questions from this particular paper, including part A, can be found in the playlist that will appear over here. questions dealing with work, energy, power, work, energy, and power, and the work energy principle can be found in the playlist that will appear over here from P1 of Cambridge. You can subscribe to my channel by clicking on this link, and I'll put the link to the part A of this question in the video, or the link that will appear at the end over here. That will take you to part A if you wanted to see part A. Thank you for watching, and see you soon.